So this is an example of a robot that journeys to a classroom where the states are journey, lost, or at the class. And some of the behaviors are move to class, avoid object, dodge student, stay right. There is a coordinator for the classes. And the perceptual schemas are the class location, the detected object, detected student, or detected path. Expressing robotic behavior. There are several methods available for expressing robot behavior, including stimulus response diagrams, a graphic representation of specific behavioral configurations, functional notation, used for clarity in the design of systems, finite state acceptor diagrams, used for temporal sequencing of behaviors, and also finite state acceptor diagrams that describe the aggregations of sequences of behaviors. A finite state automata makes a diagram that lists all of the possible inputs and outputs and the behaviors and what should happen. It's like a finite state machine where you have all the behaviors for the task, the releasers for each behavior, the function that computes the new state, the behavior that the robot starts in when it's turned on, the behaviors the robot must reach to terminate, as well as the current state and the current input. So if you think about that diagram we had on the prior page, the robot's states are either journey, at class, or lost. And then if it's not at class, then it goes to the journey state. If there's an error input, then the robot's lost. If the robot's reached class, it's at the class, that's the terminal state. Or if it's at class and there's any input, it stays in class. Or if it's lost and there's any input, the robot remains lost. Behaviors in object-oriented programming. The objects consist of data and methods, attributes and operations. A schema consists of both of the knowledge of how to act and or perceive. And in a programming language, this would be called like the class. The schema class is an optional method called a coordinated control program. The coordinated control program is a function that coordinates any methods or schemas in the derived class. Schema class has a behavior, motor schema, and perceptual schema. A behavior in a schema that consists of a perceptual schema and a motor schema would have methods for that behavior class. So behaviors are typically executed in parallel or concurrently. Networks of behaviors are used to store state and construct world models or representations. Behaviors are designed to operate on compatible timescales. Behavior-based control have the following key properties: the ability to react in real time, the ability to use representation to generate efficient behavior, and the ability to use uniform structure and representation throughout the system. It is modular by using a collection of behaviors, and these behaviors are relatively similar in times of. It is based on a reactive velocity where behaviors are incrementally added to the system and the behaviors are executed concurrently in parallel. Behaviors are activated in response to internal and or external conditions, and they're more expressive than simple reactive rules. They're more complex and more flexible than reactive rules and can be used in clever ways to program the robot. Steps to design a behavioral system. First is to describe the task, the robot, and the environment, and then how the robot should behave or act in response to that environment. Next is to describe how to implement and test or refine each behavior. Remember, you want to test each of the behaviors independently to make sure they're working correctly, and then to test the overall system together and be prepared in case there are any unexpected results, which would be an emergent behavior. Here's an example of a photophilic behavior design. Notice it looks a lot like subsumption architecture, which we've talked about before, is behavior-based control. So here we have two levels. The first one is run away, which is like our obstacle avoidance level. That's our priority in most cases, unless, of course, the move to light behavior has been triggered. And at that point, the robot is in obstacle avoidance mode, but also trying to arrive at the light. Once it arrives at the light, it would inhibit the runaway behavior because once it's at the light, you don't want it to run away from the light. And notice that the avoid behavior subsumes the runaway behavior as well because the priority has become moving to the light. The way you would represent this as a table is the releasers would be the light which is the robot's goal to get to, or the range, which would be for obstacle avoidance. So we have two behaviors, photophilic or love of light, and obstacle avoidance. The motor schema are move to light, avoid the light, or run away. And the percept is either the light, the direction and the strength, or the proximity to an obstacle. And the perceptual schema are brightness or at light and the obstacle. So what you should start to see here is how we actually design a behavior-based system using software by making the perceptual schemas functions where the percepts are inputs from the sensors. Representation in behavior-based control. Behaviors can interact with each other within the robot to store a representation. Behaviors can have their own representation, and this is how it becomes distributed about the system. And it can serve as a basis for learning and prediction, which means that they can achieve the same things as deliberative or hybrid systems, but in a different way, and the difference being in how the representations are used. To make robots flock together when they cannot communicate with each other, you have their own roles and own local sensory data and use emergent behavior. This can be achieved with the following rules. Don't get too close to other robots or obstacles, but don't get too far away from other robots or obstacles, and keep moving as long as you can. To get the robots to move to a certain destination, use another rule which moves each robot towards some goal point. Emergence depends on two components: existence of an external observer to see the behavior and describe it, and access to the innards of the controller to verify that the behavior is not explicitly specified in the system. An alternate definition of emergent behavior is a structured pattern, meaningful behavior that is apparent at one level of the system, the observer's viewpoint, but not available at the other, the controller or the robot's viewpoint. This is an example of emergent clustering and construction. And it's done by using the demo create program. Notice that the boxes start to cluster together. So now let's look at two swarm examples from Georgia Tech's GRITS lab, where the robots communicate and work in concert to achieve a task, such as playing music or spelling the letters GRITS. And this concludes today's lecture on behavior-based control. Have an awesome day.